In this segment, we'll take our first look at that built-in type classes and their instances. Here's a diagram from the wiki book about Haskell that tries to cram in all the type classes. Now, I'm going to omit some because they're not really central to what I want to talk about in this course. They're ones to do with fractional numbers. And I'm going to postpone talking about some others until another segment in a couple of weeks' time. So what I want to do here is talk about these, which cover some of the basic classes like EQ, show, read, ord, things that we've seen already, and some of the numeric type classes and how they're interrelated. So that's the diagram. Let's get started with looking at what we can find in the built-in type classes. Something that we've seen a lot is the EQ type class for equality. It's described by the interface that contains two functions. One is the equals function, the other is the not equals function. They're both of type A to bool, so they compare two elements of the same type, and for A to be in that class, at least one of those has to be implemented. And you see what's called a pragma here, the final line of the text on the right hand side. It's signaled by the squiggly bracket minus hash parenthesization, and that says a minimal implementation is either equals or not equals. And in fact, I talked earlier about how there was a default implementation of each in terms of the other. The other thing to say is that this information is given by typing :info EQ to the GHCI prompt. Let's just take a look at that, because it doesn't only give us that information, but it gives us information about all the instances, or all the instances among the built-in types. So if we type info EQ, we get screenfuls of information, but let's scroll back to the beginning. What we get is we get the definition of the class, EQ of A, and it tells us about the two functions that are in the interface in the class declaration, and gives minimal, and then it gives us a whole lot of instances. It says integer is a instance of EQ. If EQA, if A and B are instances, then either AB is an instance. If A is an instance, then maybe of A is an instance, and so on and so forth. So and towards the end of the listing, it mentions that bool, char, double, float, int, and lists and so on are all instances of EQ. So pretty much everything is an instance of EQ except function types and IO, some of the monads to do with input output. So most things have EQ instances, but not all. So ordering the class ord extends the class EQ, and you can see this in the declaration on the right, which says if A is an EQ type, then you can define an ord type if you provide the functions here. And there's a lot of comparison functions: less than or equal to, greater than or equal to, maximum, minimum, and a function compare. And we can see on the left hand side a definition of how compare works. It returns one of the three values LT, EQ, or GT according to how the first and the second arguments of compare, as it were. So that gives us the three possible outcomes in a single function call. Whereas if we want to know that just using the binary operators, less than or equal to, and so on, we need to make two comparisons, or we need to make an explicit equality comparison. This gives us the three options in a single go. And you can see again, in terms of minimality, it's enough either to implement compare or to implement less than or equals, because you can see on the left, I've implemented compare using less than or equals and equals, which we can also use because ORD inherits from EQ. And obviously it's easy to say when something is less than or equal using compare. You say that when you apply compare, the answer is not greater than. The answer is less than or equal, i.e. not greater than. So there we have the ordering. And again, if you look at info ORD in GHCI, you will see that there's a whole lot of instances of ordering. Okay. We also have types which we can think of as coming from an enumeration. We can lay them out one at a time, x0, x1, x2, and so on and so forth, like the positive integers. And you can imagine that every number has a successor, every number has a predecessor, or maybe not every number. And the minimal instance are the functions to enum and from enum that convert between the enumeration and integers. Now, they can be derived for real enumerated types like bool and compare, but they can be implemented for many other types. And you can imagine it's not terribly difficult to think about how you might want to implement them. There's another rather more minimal class called bounded. And that simply has two values attached to it. It says there are upper and lower bounds on the values in this type. There is a minimum and there is a maximum. And the minimal implementation is that you have to provide both of those. Now it's fine, it's obvious what the minimum and maximum are for a finite type, but also for int, there is minint and maxint, because int are fixed size integers. These are not integer, the type which contains all the integers. Int is bounded, and so there is indeed a minimum and maximum integer and character. So bounded provides, if a type is in the class bounded, then there are two values identified, min bound and max bound. Now, we've also talked quite a bit about show. What show does is allow us to turn a value of a particular type into a string. And the class show has a number of functions. It has a function that allows us to think about using the show function at a particular precedence. That allows you to combine it with other functions that might have a different precedence. It also allows you to print more efficiently a list of values by turning that list into a function from strings to strings. But the canonical function in the show class is the show function that takes a value of type A and turns it into a string. And that's one of the minimal ways of implementing show, the show type, the show class. And again, lots and lots of instances. You can't show functions, you can't show IO, but nearly every other type is in show. Now, and of course, show is often, when we define data types, we derive the value for show, and that prints the type out as it looks. But you can it's often the case that you might want to have a handcrafted representation, a handcrafted show function, and that's perfectly possible. You don't always have to have the derived version. You can define a version for yourself that better suits your needs, better suits the needs of a particular application. Okay, now show takes a value to a string. There is also a function read that takes strings into values. Now, what you can see here is that there is a function read that takes a string to a value. But if we use reads prec, you can see an example here of what reads_prec does. It takes, and I can say, and now of course, in order to read a string, or to read from a string into a type, I have to say which type I'm looking for. So you can see here I've applied reads_prec to 0 and the string space 1234 space, and said I want back a list of pairs of integers and strings. And what I get back is the integer 1234 and the string empty string, which is what follows that value. And a similar thing with integers. And you'll find if I say reads_prec that from 1234 a string, I find nothing comes back because there is no possible reading of that as a string, because it's not contained. There are no double quotes embedded in that string. But to be honest, we don't use read that often. It's typically if you want to do some work on reading data into a program, then you'll do some parsing yourself, as we saw when we talked about the expression case study in block 7. So reads_prec is there. It's the inverse of show, but or read is the inverse of show, but we tend not to use it too heavily. Well, I tend not to use it too heavily. I suppose that's what I'm saying. Okay, so I think we've covered all the non-numeric classes. So let's have a look at the numeric classes. There is a class num that contains ints of fixed and arbitrary size, floating point numbers, double size floats, and words, which are words made of bits. And on these we can do plus, minus, multiplication. We can turn a value to its negation. We can take its absolute value, that is, lose the minus sign if there is one. And signum gives us 1 if the function is positive, number is positive, 0 if it's 0, and -1 if it's negative. And there is a class of minimal functions that need to be implemented there. As you can imagine, you don't need both negate and binary minus. Each can be defined in terms of the other. So those are the simplest class of numbers. But there is a rather narrow extension of that, of what are called real numbers. And this is confusing because ints are not real, really, which adds this one extra function, which takes a number to a rational. We won't talk anything more about rationals in this course, but it also requires an ordering on the numbers. You can see in fact on num, there was no requirement for there to be any ordering on the numbers. When we turn that to real, we ask for real inherits from, real extends num A and ord A. So it has the functions from num A and the functions from ord A, plus this 2 rational. So now looking at integral whole numbers, we require those to be in num and ord. We get that from real, and being in enum. And if they extend all those interfaces, if they're instances of all those classes, then we also include quotient, remainder, div, mod, things for doing whole number division, and quotient, remainder, div, mod, and a conversion function that takes something of this type to a integer. Now there are other classes, fractional, real frac, floating, and real float, which I'm not going to talk about, but you can see the documentation for those, or you can get information about them by typing :info and the name of the class. But that covers all the numbers that I would like to talk about in this introduction. So we have integral, that gives us all the division functions. We have num, which gives us the other arithmetical functions.